right, we're into our last chapter. We're going to go through. We'll spend the rest of this week going through notes in this last chapter. Beginning of next week, we'll finish up anything we need to do with this chapter, have a chapter test, and then we'll do some review and prepare for the final at that point. We have until the Tuesday, the 19th, 2 weeks from today. So to get the final done, so we have time here to be able to complete everything. The last part is going into more of a thermal aspect of it. We talked about the idea of the mechanics aspect. That was the whole first half of this chapter, which is most important. This is now venturing into the end of Physics 1, beginning of Physics 2, when you go to college. The thermal aspect of what is occurring in the idea of science and physics. When you go, if you're going to become an engineer, you want to go do engineering stuff, you have 3 classes that deal with thermal aspect of it. You have Thermodynamics 1, Thermodynamics 2. You also have a class that's called Heat Transfer that allows us to be able to deal with all the heat aspects of components, because all these things are important in regards to how things are designed. Your car, for you to have your car drive and keep it in a good maintenance state, you need to have gas in it, you need to have oil in it, but you also need to have antifreeze in it, a coolant in it. You have to have a cooling system, because engines use gasoline, and they light the gasoline to be able to heat the air that's in your engine, but you're creating heat. And what occurs in your engine is when you create too much heat and you don't have any coolant in there, any fluid in there, what would happen is your engine would basically just melt down. Okay? You're going to have issues. So you have to be able to cool the engine down as you're driving 75 miles per hour down the interstate. Your engine has to cool down. When you get to a destination after driving your car for 8 hours or 6 hours or 5 hours, doesn't matter, and you go at a high rate of speed, you open up the engine hood, are you able to put your hand on the engine and just say, oh, this is nice? No, you're going to burn your hand because you have a temperature there. So engines are made and designed to be able to drive you, but they're going to heat up. But if they get too hot, it will have something will happen called overheating. So you need to be able to remove some of that heat from the engine so it can maintain an efficient manner and be able to drive you down the road. So thermodynamics aspect of it, there's a lot of it, and that's just in the car, but you can take a look at engines, you can take a look at rockets, you can take a look at anything there. You need to be able to cool those things down somehow. So there's a whole aspect of mechanics. You need to be able to cool these mechanics down somehow. Well, how you cool them down is through the thermal aspect of it. We talked about mechanical energy. The thermal energy is a non-mechanical energy. The idea of friction is a non-mechanical energy. So we have to be able to consider all these things as we go through the idea of physics and designs in the physics. The question I have for you there is, what is cold? What is cold? Okay, we say, man, it's cold, it's hot. If it's negative 10 degrees Celsius or 0 degrees Fahrenheit outside, and you walk outside in a pair of shorts and a t-shirt, is that cold? Are you cold? Go on, you walk to school in the middle of winter in a pair of shorts. Is that cold? Is it cold out there?
That's pretty cold.
It's cold. Okay? But you're wearing shorts. You could be wearing sweats, you could be wearing pants, you could be wearing, warmer clothes, but for some people, that's not very cold. It's 25 degrees outside, I'm walking into school with a t-shirt and a pair of shorts on. Oh, this is nice, it's nice out here. To me, I'm an older person, that's cold. I don't like cold, okay? I don't like cold. Well, if it gets 85 degrees outside, and you're working outside, or you're just walking outside, or you're just sitting outside, and you're sitting in the sun that's 85 degrees, or even the shade, some people might think, oh man, this is too hot. I can't take this. This is just way too hot. Well, like I said, everybody is a different person. What is hot for some people is cold for the other. What is cold for some people is hot for, is not cold for other people. So when you're talking about cold and hot, when we say the word hot and cold, we rely a lot on the personal aspect of this. So looking at going outside, if it's 100 degrees Fahrenheit or 80 degrees Fahrenheit, what is hot, what is cold? Your body is 98 to 99 degrees Fahrenheit. Your senses will dictate whether you're hot or cold. Your body temperature, if you take your body temperature, you're somewhere, if you're not sick, in the 98 to 99 degrees Fahrenheit range. When you go and put yourself in an environment that's 70 degrees, that is colder than your body temperature. So what your senses will think is, oh, this is cold. This is cold because the outside environment temperature is colder than my body temperature. Okay, so that is a sense on your skin that transmits up to your brain. Okay, so there's a whole dynamic in regards to senses going up the brain there. So when you're looking at a body temperature 98 to 99, your senses will tell you what is hot, what is cold. If it's 85 degrees outside, it's still not as hot as your body. Because your body is 98, 99 degrees. So you don't still feel that it's a little bit cooler than your body. You get up to 100 degrees, now it's a little bit warmer than your body. Okay, now it's hot. So the idea of hot and cold, a lot of it depends on your senses. Okay, hot and cold is relative concept to the senses of your object, senses of the object experiencing the situation. So once again, hot and cold is a personal thing. And we use that term hot and cold as just how we verbalize things. Things are hot, things are cold. We put an ice cube on your arm. Oh, that's cold. Okay? Why? You sense, your senses that you have on your skin transmits up to your brain. And your trigger is that it's cold. To us, 0 degrees is cold because the temperature of the body is warmer than the environment. 100 degrees is hot because the temperature of the body is colder than the environment. So once again, we as humans register things that are hot or cold compared to basically our body and the senses of our body, because we're still at 98 to 99 degrees Fahrenheit. So when you talk about hot or cold, it's a personal thing. In either case, what is determining the factor hot or cold? The temperature. the temperature is a determining factor in regards to hot and cold. And that is a good guide point of we look at our phones, we look at thermometers outside, and we see what the temperature is out there. You get up in the morning, you may look at your phone, the weather app that you may have on your phone, that tells you what the temperature is outside, as you're sitting there trying to figure out what do I want to wear today. If it's going to be 80 degrees outside, and you're going to sit there and dress in jeans and a long sleeve shirt, that's very warm. Well, you might now because we have air conditioning here because it cools down a little bit. But years ago, were you guys here when we didn't have air conditioning?
No.
It's
Our
always
freshman year was the first year we had that.
Okay, so believe me, when it was warm outside, it was warm in here. You're basically sweating bullets. Okay, I would go through a day and I'd have a nice froth that was built up in me. I was sweating. How's the temperature increase in your house? Okay, you wake up in the morning, it's middle of January, your dad probably turned the thermostat down to 67 degrees or 66 degrees to conserve energy because you're in bed, everybody is sleeping, they have blankets on top of them. The temperature of the house, they usually gets turned down at nighttime. Okay, you wake up in the morning, I know what it's like in my house just to conserve energy. It's at 67 degrees at nighttime. It's a comfortable sleeping temperature, at least for me, and for most of our household, because you know what? They got covers on, they can warm up very quickly by just putting an additional cover on. Okay, but as you wake up in the morning, mom or dad will increase the temperature in the thermostat a little bit. Okay, so what you have is you have a furnace that runs, or if you have wood, you burn some wood, you put some wood in the fireplace, and you burn the fireplace a little bit. Okay, but how temperature is added or increased in the house, energy must be added, whether it's propane, wood, oil, natural gas, sun, solar panels, if you have solar panels at your house. Okay, you have to increase the temperature in your house by adding energy. Energy must be added. Your hands are 98.6 degrees. You rub your hands together, and you create friction. And when you create friction, friction is thermal energy. Okay? So you're adding thermal energy to your hands, and your hands get warmer. You've added energy. Well, the ancient theory of how a body warms. Okay? How does a body warm? How do you get a body warmer? How does an ice cube go from ice to water? Well, it has to increase in its temperature. Okay? But what is the thermal properties behind that idea? Well, what we have is we have the ancient way of dealing with this is what is called a caloric theory. The caloric theory, an object is warmed internally by an invisible fluid called caloric. So if I had ice cube, or if you're outside and you have ice, you have snow, whatever you have on the outside in the middle of winter, and it starts to melt. The temperature raises up to 35 degrees or 34 degrees, 36 degrees, and it starts to melt. Well, what is the thermal properties behind why is it melting? Well, the initial theory was it has an invisible fluid in there. That invisible fluid internally warms the object. Just like, and what they tried to relate it to is, what is the ultimate heating and warming and cooling aspect of your body? What heats your body, what cools your body? What's being pumped through your body?
Blood.
Blood. The blood goes through your body. And the blood is the thing that warms your body up or cools your body down. Okay? So that is your heating and cooling regulatory system that you have there, is the internal aspect of your blood is going through and it cools your body down or warms it up. What they translate that into is physical properties like this desk. This desk here is the temperature of this room. So this desk here is probably 70 degrees. Okay? So if I have this body is 70 degrees, this desk is 70 degrees, if I would turn the heat on in this room and get it up to 85 degrees, this desk would turn to 85 degrees. Well, how does this desk go from 70 degrees to 85 degrees? Well, there's no blood that's pumping through there, but how does it warm up? How does it warm? How does it increase in temperature? Well, they said, well, there's an invisible fluid called caloric in there that will act like your blood and warm the object up. The problem is this is not explained. Two frozen bodies in a frozen environment, when rubbed together, create melting. If you had gloves on, so you had no temperature that's being transferred into ice cubes, and you go outside on a 20-degree temperature day, and you had two ice cubes and you rub them together, they would melt. They would melt. Why would those two bodies melt? They're frozen bodies, they're in a frozen environment. Why would those two bodies melt? So we start talking about internal energies. Energies associated with the atomic motion of a substance. We all have molecules inside of us. We have atoms, we have molecules. We have bonds that are created. Okay, we have objects that are in motion within our body. These energies associated with the atomic motion of a substance, which then transferred us to the 19th century, which is the kinetic theory. Okay, it took to the 1800s. Okay, you have all these smart people throughout history. They couldn't really explain how things and objects warmed or cooled. The 19th century came to kinetic theory. Talked about the atomic particles of a substance or motion. The temperature of a substance is proportional to the average kinetic energy of these particles. So when you talk about the kinetic theory, the atomic particles of a substance are in motion. The temperature of the substance is proportional to the average kinetic energy of the particles. So you look at all your particles that are internal to you. There's motions. You look at all the particles that are internal to this desk. Okay? You have a lot of bonds that are connected these things together, forming a solid. Okay? But they are still in motion. Even though we think they're stationary, there's still a little bit of motion that's going on there. Well, if we look at the average kinetic energy of all these particles, that's going to be proportional to the idea of temperature. The larger the mass, more particles, than the smaller mass,
but you're talking about the total kinetic energy of a larger mass is larger. Since this is an average though, we divide by the total number of particles. The average temperature will be the same in the alike environments. Just because you have more particles, yes, you'll have more kinetic energy. But when you take the average of that kinetic energy, you divide by your total number of particles, you're going to come down to the exact same as a smaller object. Temperature is independent of the size and number of particles of the object. Temperature is independent of the size and number of particles of the object. We're also going to talk about thermal equilibrium. Two or more objects and the environment achieve the same temperature when placed in that environment. When things that are in contact with each other achieve the same temperature. That's what's called thermal equilibrium. If you take a look at these desks are in contact with the environment of this room. So these desks are going to assume the temperature of this room. Okay, anything that we have in here is going to assume the temperature. A couple weeks ago I poured this water into this beaker. Okay, it is in contact with this room. So this temperature of this water is also the temperature of this room. They have achieved thermal equilibrium. If you would put ice cubes in a glass of water, you put ice cubes in a glass of water, they will eventually melt. You get water out of the tap, you put ice cubes in there to cool it down. They will achieve a thermal equilibrium at some point. It will be a temperature that is lower, which is what is a little bit more appealing to humans. Nobody likes to drink a warm glass of water. Okay, once again, the kinetic theory. Your temperature, the temperature of the object is proportional to the average kinetic energy of the particles of the objects. Okay, so how you look at the idea of temperature. You can also look at the average kinetic energy of all the particles that are there. A thermometer is a device that's placed in contact with an object. To achieve thermal equilibrium. You're not feeling well. Your parents may ask you to take your temperature, or you may do it yourself. Well, how do you take your temperature? Well, you get your thermometer out, you put it in your mouth. You turn it on first. You put it in your mouth until you hear this, and then you pull it out. And then you look at the temperature. Okay? What is occurring there is the thermometer is achieving a thermal equilibrium of the area underneath your tongue, which is a good temperature or a good indicator of the temperature of your body. Okay? If you want to cool, if you want to not have a temperature, drink a glass of cold water first, and then put the thermometer in your mouth. You won't have a temperature. It will be below normal. Okay, so if you want to play the trick. Okay, so when we talk about thermometer, we put a thermometer in an environment and we achieve the thermal equilibrium. Your thermometer that you have outside your house, okay, it will achieve thermal equilibrium with the environment outside your house. The liquid within the thermometer will either expand or contract. When you heat objects, they tend to expand. Well, most thermometers, at least old school thermometers, have a red liquid in there, which is what? Mercury. Okay? If you heat mercury, what will happen is it will expand. If you cool mercury, it will contract. And it will go up and down as a device, which is called a thermometer. You either expand or contract, so it will give you a temperature. A thermometer is calibrated to measure the temperature of an object due to the amount of expansion or contraction of the liquid. Most of the time most thermometers are filled with mercury. But some are filled with alcohol. They're most accurate when temperatures are between boiling and freezing. Newer thermometers are electronic and heat sensors. Technology has improved immensely. Alcohol tends to be a little bit more accurate on the outside, or when you get to more of the extremes. Mercury is pretty good between boiling and freezing. But once again, the newer thermometers, they're just heat sensors. They are electronic and they're heat sensors, and it's just how technology has gone. And some of the reason why is the old school thermometers of mercury, you put mercury in your mouth. Basically, a thermometer is filled with mercury. Okay, if somehow the mercury broke, or the thermometer broke, you may get mercury within your mouth. Okay, or if you drop a thermometer, you have mercury on the floor that beads up. Okay, and you have to be able to clean that up. So you start running into issues with respect to health issues, and that's why what we have talked about with respect to you put it in your mouth, and that's more of a heat sensor that is there. It's a little bit better, safer for the environment and also the people. We can also have gas thermometers. Outside the freezing and boiling range, gas thermometers are more accurate hydrogen helium field. So you have a helium filled or a hydrogen filled thermometer. Temperature scales are set and calibrated and are dependent on the freezing and boiling point of water at sea level and at standard atmospheric pressure. So when you talk about temperature scales, the basis of all temperature scales is your freezing and boiling points of water at sea level, because if you go up above Denver, or like in Denver, the Mile High City, your boiling point decreases. So you start running into issues with respect to higher elevations because the pressure is a little bit different. But we have to have standard atmospheric pressure, and we're going to be at sea level. finish the front side here and we'll be done for the day. We talk about a degree. Degree is a division on the thermometer. Degree is a division on the thermometer. We are English and we are American, so we still deal with the Fahrenheit scale. I think there's only, if I remember correctly, 3 countries in the world that deal with and work with temperature in the Fahrenheit scale. Everybody else has changed to the Celsius world. We tried to change, once again, going back to Jimmy Carter, to change everything to the metric scale, and that was included the thermometers, the bank thermometers that used to flash the time and then the temperature, and then it would do time and temperature. And even if you go out to our main board out here on 94, you have time and temperature. Okay, the temperature is only in Fahrenheit, but what the banks used to have is time, temperature in Fahrenheit, and then temperature in Celsius, metric. Then go back to time, Fahrenheit, Celsius, time. So they were trying to transition into the idea of metric world and Celsius, but it just never stuck. It never stuck. Like I said, there's 3 countries, I can't remember. One's in South America, and I think one's in Asia. The rest of the world still deals with the Celsius world, or Celsius temperature. Now, the Americans, in the scientific world, the Americans will deal with temperatures in Celsius. Okay, they will still, everything in the scientific world in America is Celsius. But in the human aspect of Americans, we just don't want to transfer into the Celsius world. We keep it in Fahrenheit. But Celsius scale, it's a metric scale named after Andrew Celsius. It's sometimes called the centigrade scale. Because everything in the metric world is based on factors of 10. Well, the Celsius scale is based on that, but it's a factor, it's called the centigrade scale, is based on the factor of 100. Where we go from 0 to 100 degrees, we have 100 degrees Celsius. We have freezing. And we have boiling of water. 0 degrees Celsius is freezing of water. 100 degrees Celsius is boiling of water. Where here we have freezing, we have boiling. We have 32 to 100, 212 degrees. We can deal with conversions. For every 1 degree Celsius rise, 1 degree rise in Celsius, this is 1.8 degree rise in Fahrenheit. So for every Celsius degree goes up 1, that means our Fahrenheit degree scale goes up 1.8. And now we can convert from Fahrenheit to Celsius. As we are in Celsius, we can multiply it by 9.95 or 1.8 and add 32 to it. So if we take 1.8, if it's 50 degrees Celsius, this would be 9/5 times 50 plus 32. So we would have 122 degrees Fahrenheit. Taking our 9/5 times 50, gives us 90 plus 32. Kinetic energy of atoms must be positive. If a substance has a negative temperature, the average kinetic energy must be positive. Kinetic energy is a scalar quantity. And we'll talk about what occurs, how do we deal with this, because all of our kinetic energies are going to be positive. All of our kinetic energies will be positive. How do I get a negative temperature? How do I get negative 5 degrees Celsius or negative 10, how do I deal with that? And we'll talk about that tomorrow, how that is dealt with. But the average energy of kinetic energy of atoms, is a substance has a negative temperature, the average kinetic energy must be positive. Kinetic energy is a scalar quantity. How do we deal with negative temperatures if all your kinetic energy is going to be positive? We will stop there today. A lot of this initial stuff is just basic terminology that we have to go with respect to the thermal aspect of physics. So we will stop there today. We will pick up there tomorrow.